Welcome back to this series on topology. In today's video, we'll be proving the closed map lemma and then seeing how useful it is in a series of examples. As always, you can find a playlist containing all the videos in this series by clicking on the info thing that should appear right now. Also, if you enjoy these videos, please consider liking them so that other people can find them more easily. Let's dive straight into the statement of the closed map lemma. So we suppose that we have some continuous map F that goes from a compact space to a Hausdorff space. So this is the setup we need for the closed map lemma. Then we can draw the following conclusions. First of all, F is a closed map under these hypotheses. Moreover, if F is surjective, then F is in fact a quotient map. If F is injective, then F is a topological embedding. And finally, if F is bijective, then F is in fact a homeomorphism. These three last points are just a consequence of F being closed under these circumstances, so really the meat of this proposition is the fact that if we have a continuous map going from a compact space to a Hausdorff space, then that map is always closed. So let's start by proving this first point, namely that F is a closed map under the hypotheses given. As you will see, the proof will rely heavily on the properties of compact spaces we proved in the last couple of videos, so I'll be reminding you of those during the proof. However, if you really want to understand the proof, it's good if you go back and review those properties if you don't remember them. All right, for the proof, we're going to fix some notation. So we're going to suppose that F goes from a space X to a space Y, with X being compact and Y Hausdorff. And of course, F is continuous. Now our goal is to show that F is a closed map, which means that it takes closed subsets in X to closed subsets in Y. Hence we will let A be some closed subset of X. And now we need to show that its image, f of A, is closed in Y. Now we know that A is a closed subset of X, and moreover X is a compact space. And we saw in the previous video that closed subsets of compact spaces are again themselves compact. Therefore, since X is compact and A closed, we conclude that A is compact. Okay. But now, if A is compact, then its image under this continuous map F will again be compact by another property of compact spaces. So then f of A is also compact, since it is the image of a compact subset under a continuous map. Finally, we now have a compact subset, namely the image f of A, in the space Y, which is Hausdorff, and the final property of compact sets we'll need is that compact subsets in Hausdorff spaces are always closed. This is also something we saw in the last video. Hence, because Y is Hausdorff, we can conclude from the fact that f of A is compact that it must also be closed. Okay, and with this we're done because we've chosen an arbitrary closed subset of X, and we've now shown that its image under F is closed, which means that F is a closed map. So as you can see, this proof was pretty simple, but it made heavy use of the properties we proved in the last video on compact spaces. In particular, we need the fact that closed subsets of compact spaces are themselves compact, that images of compact spaces under continuous maps are again compact, and finally, that compact subsets of Hausdorff spaces are closed. Now, usually we're not particularly interested in whether maps are closed or not, but it turns out that the property of being closed is a nice intermediate property for other properties of continuous maps that interest us more. For example, them being quotient maps or homeomorphisms. Thus, in the next parts of the proposition, we'll use the fact that F is closed to show that under additional assumptions on injectivity and surjectivity, that it's then one of these special types of maps. The The first thing we're going to show is that under the assumptions of the closed map lemma, if f is additionally surjective, then f is in fact a quotient map. For the proof, we note that by part A of the proposition, f is closed, and now we need to use the fact that f is closed and surjective to show that it's a quotient map. If I remember correctly, we already proved this in a previous video, but I'll do the entire proof again because that's been a long while back. As a reminder, I'll briefly explain again what it means to be a quotient map. So if we have some space x and another space y, and a continuous map going between them, then this continuous map here is a quotient map if first f is surjective, and second, we need that a subset of y is open in y if and only if its preimage is open in x. So some subset u of y is open if and only if its preimage, f inverse of u, is open in x. In other words, being a quotient map means that the topology on y is basically the quotient topology induced by this map f. Okay, so let's proceed with proving that f is a quotient map. So we know that f is surjective, so that's our assumption here. So the only other thing we have to prove here is that subsets of y are open if and only if their preimages are open in x. Now, since y is continuous, we know that one direction of implication holds, namely that if we have an open subset in y, then its preimage is open in x. That's just the definition of continuity. Hence, the only thing we have to prove here is that whenever we have an open preimage of some subset in x, then the original subset in y is also open. Okay, so we let u be some subset of y such that its preimage is open in x. Perhaps I can draw this in the picture, so this would be some subset u here. And now we look at its preimage under f, and our hypothesis is that this preimage here, f inverse of u, is open. Now our goal will be to show that the original set u was actually open to begin with. Okay, what do we know about f? Well, aside from it being surjective, we also know that f is closed. And how can we get a closed subset here in this picture? Well, we know that this preimage, f inverse of u, is open, and this means that its complement will be closed in x. So in yellow, I'm drawing in the complement of this preimage. Therefore, since f inverse of u is open, we know that its complement is closed. So hence, f inverse of u complement is closed. And now, because f is closed, we know that also the image of this complement will be closed in y. So the image under f of this complement is closed in y as well. Now let's think about what this image looks like. So we're mapping the yellow set here under f, and we know that the yellow set is the complement of this red set. And moreover, the red set is itself the preimage of this red set on the right here. This means that this yellow set has to be mapped into the complement of the red set on the right. So I'm drawing here schematically the image f of f inverse of u complement. So my claim here is basically that this image set is equal to u complement. I'll just explain why this is the case in words. So first, let's consider the left to right inclusion. So we suppose that we have some point which lies in this image of the complement of the preimage of u. And now we want to show that it lies in u complement, which is equivalent to just showing that it does not lie in u. So suppose we had some point in this yellow set here on the left which mapped into u. Well, then by definition it would lie in the preimage of u. And well, the preimage of u is this red set here on the left, and the yellow set is its complement. But now we have some point in the complement of the preimage which also lies in the preimage, which is a contradiction, and therefore every point here on the left has to be mapped outside of U. Okay, so that establishes the left to right inclusion. And conversely, we have to argue that every point in U complement is contained in this image set on the left here. And essentially the reason for this is the fact that F is surjective. So if we pick some point in U complement, so some point that does not lie in U, well then there has to be some point in X which maps to it. And moreover, that point in X can't lie in the preimage of U because our original point was outside of U. Hence this shows there must exist some point in X which lies outside the preimage of U, so some point in the complement of this preimage which maps to that point which was in U complement. And that argument establishes the reverse inclusion, and therefore these two sets are in fact equal. If you had trouble following this argument, I suggest you just pause and think through it slowly for yourself to make sure that this makes sense. Okay, so we're almost done. Let's return to the main thread of the argument. So the thing we want to prove is that under the assumptions of the closed map lemma, namely that we have a continuous map from a compact space to a Hausdorff space, if that continuous map is in addition surjective, then it is in fact a quotient map. And we recalled that being a quotient map means being continuous, surjective, and moreover that every subset that is open in the codomain space Y is open if and only if its preimage is open in X. Now we already have that F is surjective and continuous, which means that one direction here in the bottom holds, namely that whenever we have an open set, its preimage is open. Hence the only other direction we need to prove is that whenever we have some set U in Y, whose preimage is open in X, then we need to show that it's actually itself open in Y. So we took such a set, we suppose that its preimage in X is open, then we looked at its complement, which is by definition closed. And now because F is closed by part A of the closed map lemma, we conclude that the image, so this image of the complement of the preimage, is closed in X. And now I've shown that this image is actually the same as U complement. So this means that U complement is also closed because it's equal to this image of a closed set under a closed map. And this then in turn implies that U is open. And this is all that we needed to show in order to prove that F is a quotient map. Okay, so we see that the argument is a bit convoluted because we're taking preimages and then images of preimages and so on, but basically the strategy for the proof is completely straightforward. We just assume the things we need to assume and more or less directly get the conclusions out of the properties we've established for F. Finally, we'll be proving the last 2 points in the closed map lemma together because they're fairly similar. They state that, well, if in addition to the hypotheses of the closed map lemma, if F is injective, then F is in fact a topological embedding, and moreover, if F is bijective, then it is a homeomorphism. We're going to start by proving part D, and then see that part C is actually a special case of part D. So for the proof of part D, we're going to suppose that F is bijective, and now it'll turn out that in fact part D will follow basically by what we saw previously in part B, because if F is bijective, it means that it's in particular surjective, and then by part B, this implies that F is a quotient map. So by part B, F is a quotient map. So what does this mean? It means that whenever we have some subset U of Y open in Y, then this is the case if and only if its preimage, F inverse of U, is open in X. So I'm using the same notation from the previous part. So F is a continuous map going from some space X to some space Y. Okay, so in pictures here, what's happening, we have some set U, which is open in Y, and we have its pre-image here under F in X. So this is F inverse of U. So we have that one is open if and only if the other is open. Now, why is this relevant for part D? Well, whenever we have a bijective map which satisfies this property, this is exactly a homeomorphism. Recall that one way to define a homeomorphism is to say that it's a continuous map that has an inverse that is also continuous. Now, if f is bijective as a set function, then this means that it has a inverse, f inverse, but we aren't guaranteed that this inverse is continuous in general. What does it mean for this function f inverse to be continuous? Well, it means that whenever we have an open set in X, then the pre-image under f inverse needs to be open in Y. Suppose that we have some set, let's call it V, being open in X. Now, since f inverse is the inverse to f, we know that if we first do f and then f inverse, this is the same as the identity on X. So since f inverse after f is equal to the identity on X, we have that V is actually equal to f inverse of f of V. Okay, why is this useful? Well, this f of V here, this is just some subset U of Y. Okay, but now by our equivalence up here, whenever we have some pre-image of some subset in Y which is open in X, then we get to conclude that this original subset U was actually open in Y. So we are assuming that V is open, so we know that the pre-image here of this set in Y is open. So this is some U, and this allows us to conclude with this implication in this direction that then U in Y is open. So in our case, this means that f of V is open in Y. Okay, but what is f of V? Well, f of V is just the pre-image of V under the inverse f inverse. So another way to think about this is whenever your function is bijective, then taking pre-images is just the same thing as mapping in the opposite direction with the inverse function. Now in our case, we're interested in f inverse, so mapping in the opposite direction with the inverse function is basically just mapping forward with f. Let's recap what we've done. So we started with some open set in X, and then we used the fact that f has a set theoretic inverse together with this property we established above, which follows from the fact that f is a quotient map, to prove that the pre-image under the inverse of that open set is again open. Okay, so all of this together implies that f inverse is continuous. Since we started with some open set in its codomain and proved that its pre-image is open in the domain. Okay, so this is again a bit complicated with all the moving forward and back with the inverses and so on. Essentially, I could have stopped the proof here because this property for a bijective function is the same as being a homeomorphism. I just explained down here why this is the case. If you had trouble following this bit down here, maybe you can go back to the video on homeomorphisms because there I think I explained this in more detail. In any case, the upshot is basically the property we need for a quotient map is exactly the same property we need for a homeomorphism, just in the case of a homeomorphism, f needs to be bijective, while in the case of a quotient map, f just needs to be surjective. Therefore, a bijective quotient map is basically almost by definition a homeomorphism. Okay, so the final thing we'll prove is part C, which says that under the assumptions of the closed map lemma, if f is in addition injective, then f is in fact a topological embedding. For this, we need to recall what a topological embedding is. So we suppose that we have a continuous map going from a space X to a space Y. So f is continuous. And well, now for it to be a topological embedding, we need two things. First, f needs to be injective. And second, f needs to be a homeomorphism onto its image. So I'll write this f homeo onto f of x. So what does this mean? Well, f will map x injectively into y. And now we want that if we restrict f to its image, f of x, so that's this orange set here, that the restricted map is in fact a homeomorphism. A homeomorphism with respect to what topology? Well, with respect to the subspace topology on the image f of x. So I mentioned before that part C is basically a special case of part D, and the reason for this is that we need to prove that f is a homomorphism onto its image f of x. One way to do this is to argue that the image space here, f of x, is again Hausdorff, which means that we can apply part D of the proposition, because if we restrict f to its image, it will be bijective, and we still have the assumptions fulfilled for the closed map lemma, and in that case f will be a homomorphism, just restricted, and this will prove that it's in fact a topological embedding. Okay, so I'll write this like this. Note that f of x, which is a subspace of y, is again Hausdorff. We just need to think about why this should be the case. So the claim is that whenever we have a subspace of a Hausdorff space, that subspace is again Hausdorff. Remember that being Hausdorff means that whenever you pick two distinct points in your space, then you can find open neighborhoods around each one respectively that are disjoint from one another. Now by hypothesis, the space Y is Hausdorff. So now we just need to argue that this means that the subspace f of x will again be Hausdorff. Okay, so we pick two distinct points in the image f of x, and we now need to find open sets in the subspace topology that are disjoint and contain one of each points respectively. Okay, now since y is Hausdorff, we can find an open neighborhood of each point, and these open neighborhoods are disjoint from one another. Now, how do we get open neighborhoods in the subspace from this? Well, we just intersect these open neighborhoods in Y with the subspace. So recall that a set is open in the subspace topology if it's an intersection of an open set in the larger space with the subspace. So in our picture, these intersections would be the things I'm drawing here in purple. Now, because the original sets, the blue ones, were disjoint in Y, it means that the intersections will also be disjoint in the subspace. Okay, so that was a quick argument for why subspaces of Hausdorff spaces are again Hausdorff, but if this doesn't convince you, you should think about this for yourself a bit longer. All right, we now look at the restricted map, which I'll call f bar, which goes from x to its image, f of x. So this is now a continuous map going from a compact space to a Hausdorff space. So this f bar satisfies the hypotheses of the closed map lemma. So this is continuous going from a compact space to a Hausdorff space. So this means by part D that f bar is in fact a homeomorphism. So f bar is a homeomorphism. And this is exactly what it means for the original map f to be a homeomorphism onto its image. Now by assumption f is injective, so that's a check, and now we've just shown that f is a homeomorphism onto its image. So this means that then f is in fact a topological embedding. Okay, so I hope this was reasonably clear. So in summary, whenever we have a continuous map going from a compact space to a Hausdorff space, we can conclude that it's closed. And moreover, if that map is in addition surjective, then it's a quotient map. If it's in addition injective, it's a topological embedding. And if it's in addition bijective, then we know it's a homeomorphism. Now I hope you can already imagine why this closed map lemma would be useful, but to drive the point home, we'll see a bunch of examples where it makes our life a lot easier. The first example is something we've already seen, namely that the unit interval quotiented out by its endpoints is homeomorphic to the circle. So the picture you should have in mind here is that we have this unit interval going from 0 to 1 as a subset of the real line. And now we're identifying the endpoints 0 and 1, and what we get is homeomorphic to the circle S1. Since we'll be making heavy use of the universal property of quotient spaces, I'll briefly remind you of that. So the universal mapping property for quotients goes as follows. So the setup is that we have some topological space X, and then we have a quotient of X, which I'll call capital Q, and along with a quotient, we always have a quotient map small q. So remember that a quotient map here is a surjective continuous map that induces the quotient topology on Q. And what does this mean? Well, it means that a subset of Q is open if and only if the pre-image under this quotient map is open in X. Now, the universal mapping property for quotients concerns whether certain maps out of X descend to maps out of Q. So if we have some continuous map going from X to T, I'll call this F, then the question is, can we somehow make this into a map going from Q to T? And now if you think about what would obstruct this process, so we have some map going out of a larger space X, and we want to somehow convert it to a map going out of a smaller space Q where certain portions of X may have been identified. So the problem is that if we have two distinct points in X, which map to two distinct points in T, and moreover, these two distinct points in X become identified in Q, so we just have a single point, then we don't know where to map this single point to. Because on the one hand, in order to make this diagram commute, we would have to map it to, say, the left point, because this point here is being mapped to this point, so we should map it to this point. But on the other hand, also this point is being mapped to this point, which should therefore be mapped to the rightmost point. So there's basically 2 points we would have to map this single point in Q to, so we can't complete this diagram with a function from Q to T, making the diagram commute. Okay, so that's what could obstruct this process of converting a map going from X to T to a map going from Q to T. Basically, we're identifying certain portions, and somehow the map F here is not allowed to map distinct points which become identified to distinct points in T. Now, what the universal mapping property for quotients is saying is that basically this is the only thing that can go wrong. So in other words, if we don't have this situation, so where two distinct points in X which become identified in Q get mapped to distinct points in T, then in fact the continuous map F from X to T descends to a continuous map from Q to T, which I'll call F bar, and moreover it does so uniquely, so there's a unique map F bar going from Q to T, which makes this diagram here commute. Let's maybe write this condition down so it's absolutely clear when this happens. The condition is that whenever we have that X is equivalent to some point Y in Q, then F of X is equal to F of Y. So this means that whenever we identify 2 points, X and Y, in the quotient space, then F has to take the same value on these 2 points. And this condition prohibits there from being 2 distinct points in X which become identified in Q that have different values under F, and well, this we saw before was the obstruction to having F descend. Okay, and again, whenever this condition is fulfilled, then there exists a unique continuous map F bar going from Q to T, making this diagram commute. And uniqueness is important for the following. Namely, we're going to use this universal property of quotients in order to show that 2 spaces, which are both quotients of a larger space, are homeomorphic to one another. For this, we suppose we have the following situation. So we again have some large space X, and now we're going to have 2 quotients of X. So we have some quotient map, let's call it Q1, going to a quotient space Q1, and we have another quotient map, Q2, going to a quotient space Q2. We now want to find conditions on the quotient maps Q1 and Q2 that will make the resulting quotient spaces capital Q1 and capital Q2 homeomorphic to one another. So in general, of course, a space X can have many different quotients which aren't homeomorphic to one another. Just think about one quotient identifying all the points in X and the other one doing nothing. So if X is not homeomorphic to a point to begin with, then these two quotient spaces would not be homeomorphic. However, we want to say that whenever Q1 and Q2, these quotient maps, make the same identifications, so identify the same portions of X, then the resulting quotient spaces will be homeomorphic. So let's now suppose that these two quotient maps, Q1 and Q2, make the same identifications. So what does this mean? Well, it means that Q1 of X is equal to Q1 of Y. So this means that Q1 would identify X and Y. This should happen if and only if Q2 makes the same identification. So Q2 of X is equal to Q2 of Y. A more suggestive way of writing this would be the following. So we could write X is equivalent under the first quotient to Y. So this is basically transforming this identification under the quotient map into an equivalence relation on the space X. We say that 2 points in X are equivalent if and only if their images under the quotient map Q1 are identified. And similarly, we could write in the bottom, this would mean X is equivalent under Q2 to Y. So basically we're saying that the two quotients make the same identifications in the sense that the same points are being set to be equivalent under both. Okay, now if you compare this to what we had above in the condition we need in order to apply the universal property of quotients, it's basically the same thing but going in both directions. So I've sort of mixed notation here, so I wrote X equivalent to Y. This basically means that Q of X is equal to Q of Y. So these are just two different ways of thinking about what quotient maps are doing. So it's saying the condition in order for the map f from x to t here to descend to a map from q to t is that whenever Q of X equals Q of Y for any 2 points small x and small y in the space capital X, then also f must identify these points. So now we're going to apply this universal property for quotients to this diagram down here, but in two ways. So in the first way, we're going to view Q1 as the quotient map Q and Q2 as the continuous map F in the diagram above. Now, in order for Q2 to descend to the quotient Q1, so this means in order for us to get some map going from Q1 to Q2, what do we need to be satisfied? Well, if we look up in the universal property here, we need that whenever the x and y are identified under this quotient map we're considering, namely Q1, then also f of x has to be equal to f of y, but in our case, f is equal to Q2. So what this condition here is saying is that, well, whenever Q1 of x is equal to Q1 of y, then Q2 of x needs to be equal to Q2 of y. And that's just this direction of the implication we've supposed in our hypothesis. Therefore, we get a unique map, Q2 bar, which is the map that Q2 descends to. But now our hypothesis here had an equivalence, so we had two directions of implication. And now we can use the other direction by viewing Q2 as the quotient map Q in this diagram and viewing Q1 as F. And maybe it's even better to sort of redraw our space Q1 over here and our map Q1 here so that we have the same ordering. So now Q2 is Q and Q1 is F. And what condition needs to be satisfied in order for Q1 to descend to this space Q2 along the quotient map Q2? Well, we need that whenever Q2 identifies certain things, so whenever Q2 of x is equal to Q2 of y, then Q1 of x is equal to Q1 of y. And that's just this direction of implication here in our hypothesis. Okay, so therefore also Q1 descends to a map Q1 bar from the space capital Q2 to the space capital Q1. And now I could have drawn this in the original diagram going in this direction, but here it's a bit clearer how we're applying the universal property. Okay, so now the final step of the argument will be to show that these maps we've obtained, Q2 bar and Q1 bar, are in fact homeomorphisms, which will then prove that the spaces capital Q1 and capital Q2 are homeomorphic to one another. So in order to prove that these are homeomorphisms, they need to be, well, continuous maps which are inverse to one another. We already know that they're continuous, so we just need to show that they're inverse to one another. Let's consider first the direction where we compose Q1 with Q2. So we're considering Q1 bar after Q2. And this is a map going from capital Q1 to capital Q1, which is already good. And we now need to show that this is in fact equal to the identity. So the fact we're going to use is that the universal property here gives us a unique map, making this diagram here commute whenever this map is able to descend to the quotient. Now, because Q2 was obtained via the universal property, it'll make this triangle here commute. So that's this map, and then this map is the same as this map. And similarly, because Q1 bar is obtained via the universal property, this triangle here commutes. And now we have sort of two commuting triangles glued to one another. And this then implies that this composition here, which I'm drawing with the red arrows, so that this whole outer triangle commutes. And well, if you look at what we were composing here along the bottom, that's just this composite map Q1 bar after Q2 bar. Therefore, this triangle here, so doing first Q1, then the composite Q1 bar after Q2 bar is the same as doing Q1. Therefore, this map here makes this outer triangle commute. The second thing we need to observe is that we can apply this universal property here to the maps Q1 and Q1 itself. So we can plug in Q1 for Q and Q1 for F. And, well, trivially, this condition is satisfied because this is just saying that Q1 makes the same identifications as itself. And therefore, there is a unique map going from Q1 to Q1, which makes this outer triangle commute. Well, we already know that this map here we have obtained as a composite of Q1 bar and Q2 bar makes this outer triangle commute. So in fact, this thing here has to be what Q1 descends to along itself. On the other hand, if you just plug in the identity here, so we have another map, namely just the identity going from Q1 to Q1, this also makes this triangle commute. Simply because if you do Q1 and then the identity, that's just the same thing as doing Q1. Now, because this map here we get from the universal property is the unique map which makes this triangle commute, and we have now two maps which make this outer triangle here commute, this means that these two maps must in fact be equal. Okay, so in fact this composite here has to be equal to the identity on the space capital Q1. Okay, so we've proved that one direction of composing these two maps, Q2 bar and Q1 bar, is the identity, and the other direction is exactly the same argument, just with the orders reversed. Okay, so in summary, we can conclude from this abstract argument that whenever we have two quotient maps, Q1 and Q2, which make the same identifications, so this condition holds, then we have that their quotient spaces are in fact homeomorphic. Now, since this was only meant as a recap, I did this pretty fast, so if you weren't able to follow all the details and you haven't seen the quotient space universal property yet, you should probably go back and watch my videos on quotient spaces. But I hope that even if you haven't seen it, this gives you some idea of where this thing we're going to be using all the time for the following examples comes from. Okay, so now with this recap out of the way, we're ready to use this together with the closed map lemma to prove this homeomorphism here. And you'll see that it's pretty quick now that we have all this background material. So the key to prove this is to use what I just showed before, namely that if we have two quotient maps out of a given space which make the same identifications, then the two quotient spaces are homeomorphic. And here the general space we'll be mapping out of is just the unit interval. And this follows naturally because one of the spaces we're looking at here is already a quotient of the unit interval. Okay, so the situation we're looking at is the following. We have this unit interval, so just as a reminder, this is the closed unit interval, so going from 0 to 1. And then we're considering the quotient, where we identify its endpoints. So 0 is equivalent to 1. And we have some quotient map Q here, which performs this identification. So Q is the identity everywhere except on the endpoints. We just have that Q of 0 is equal to Q of 1. On the other hand, we can also map this closed unit interval to the circle by the exponential map. So this is the map that takes some x and maps it to 2 pi times I times x. So here we're thinking of the unit circle as a subset of the complex plane, and then this exponential map here will map any point in 0 and 1 and to some point in this unit circle. Now suppose for the moment that we knew that this exponential map here was a quotient map. Well, then we have the situation that I set up before. So if you consider what identifications does Q make here, well, it just identifies the endpoints 0 and 1. And now let's consider the exponential map and think about what points this identifies. So we're thinking of the circle as a subset of the complex plane. And well, then this argument here, so 2 pi x, that's exactly going to be the angle we're considering. So we have some angle phi. And in our case, this is going to be given by 2 pi times x, where x is some point in the unit interval. And well, then this point here that I've drawn, this is going to be exp of phi times I. Now, if you think about us going around the circle, so increasing the angle, so we start with x is equal to 0. There, our image point under the exponential map is here, and then we increase x up until the point where x is equal to 1, and then the angle becomes 2 pi. Remember, we're multiplying by this factor 2 pi here, and at the point where x is 1, our angle is 2 pi, and we're again at the same point we started at. So you can see from this visual argument that the exponential map will only identify points 0 and 1, but all the other points remain distinct around the circle. Therefore, both Q and this exponential map here make exactly the same identifications, namely they only identify the endpoints, and on the rest of the interval they're injective. And now if we knew that both of them are quotient maps, then we could apply what we saw previously and conclude that this quotient here of the unit interval is homeomorphic to S1. Okay, so the only stumbling block is that we don't necessarily know that this exponential map here is a quotient map, and that's where the closed map lemma comes in. Now, if you wanted to prove that this is a quotient map from scratch, the argument would be really involved, because you'd have to prove that a subset of this space S1 is open if and only if the pre-image under this exponential map is open in I. Now, in both cases, I is a subspace of the real line, and S1 we're thinking of as a subspace of the complex plane, so R2. And, well, you have to take an arbitrary, say, open set in this subspace, which you have to think about first what that means, and then pull it back along this map and look at its pre-image, and then you have a bunch of special cases where either the subset goes out across the boundary or not, and so on. So this is very, very tedious. However, now in the case where we have the closed map lemma, we can just show that our source space is compact and that our target space is Hausdorff, and moreover, we need this map to be surjective, and then we can conclude that it's a quotient map. And well, the setup here is exactly what we need, because the closed interval from 0 to 1 is compact. For example, we saw in the video on compactness that a subset of Euclidean space is compact if and only if it's closed and bounded. So here we indeed have a closed and bounded subset of the real line, so it's compact. And now we need to argue that S1 is Hausdorff. And well, we can do this because we know that R2 is Hausdorff, and well, S1 is considered as a subspace of R2. And we saw previously in this video that whenever we have a subspace of a Hausdorff space, then it's itself Hausdorff. The last thing we need to do is show that this map here is surjective, but if you know what the exponential map does, then you can see that, well, it maps this closed unit interval all the way around the circle, so every point in the circle is covered. If you wanted to do this more formally, you would pick some point in the unit circle, and then we need to find some point in this unit interval that maps to it. Well, then we just consider the angle here, divide the angle by 2 pi, and well, that will be the point x, which maps to this point under the exponential map. Okay, so we now have a surjective map from a compact space to a Hausdorff space, which allows us to conclude that it's a quotient map. So we write since exp 2 pi I x is a continuous surjective map from a compact space to a Hausdorff space, it is a quotient map. So this is one of the parts of the closed map lemma we proved just before. And now, as I argued in the first part, well, Q and this exponential map make the same identifications, namely they only identify the endpoints of the interval. So since Q and exp 2 pi I x make the same identifications, it now follows that their respective quotients are homeomorphic to one another. So we know that now this I, where we identify the endpoints, is homeomorphic to S1, using this consequence of the universal property of quotient spaces. All right, so I spent a long time recapping the universal property of quotient spaces and also explaining how to use this together with a closed map lemma to conclude this homeomorphism here. And you may be thinking, okay, well, you could just prove this directly. And in this case, you're probably right that it would be maybe not so bad to construct explicit homeomorphisms between these spaces and prove that they're inverse to one another and continuous and so on. However, this argument here is like a general strategy that works for these types of situations, and it scales quite nicely with the complexity of the spaces appearing here. So when these spaces get more complicated, it might be much more difficult to explicitly see what the homeomorphism is you need to construct. However, this type of argument will still work. So let's apply this general scheme again in a bit more complicated example. So here we're going to prove that a certain quotient of the unit square is homeomorphic to the torus. And how do we quotient the unit square? So their unit square is just the unit interval producted with itself. And we're going to identify the boundaries. So we are identifying this boundary here with this boundary on the opposite side, but in the same direction. So some point here would be identified with a corresponding point on the other side. And similarly, we'll identify the top boundary with the bottom boundary, again in the same direction. So for example, this point here would be identified with that point. Now, if you think about geometrically what's going on, so if I first identify, say, this boundary with this boundary, what I get is like a tube. So you can think about this square here as being a piece of paper, and now you're folding it around so that these two sides touch one another. And the result is that you get like some sort of tube. Let me see if I can draw this nicely. So here we would see the edge, here we would not see the edge, and then we'd have this bit where we've identified this boundary with the one arrow going like that. And now the other two boundaries are still present, so these boundaries are now these circular boundaries of the tube. So here we still have two arrows going up like this. And well, now we need to identify these remaining boundaries with one another going in the same direction. And the way to do this is to sort of pull these edges of the tube around and sort of form a donut shape, and then glue the remaining boundaries together. So let's see if I can draw this. Maybe I'll just go ahead and draw a torus. Okay, so if we have glued the final edges, it'll look like this. So we'll have sort of a circular place here where we've glued the edges with the 2 arrows, and now the place where we've glued the first edge will be like a circumference of a torus. Okay, so this type of visual argument should convince us that this homeomorphism is plausible, but now we need to actually prove it rigorously, and we're going to use exactly the same strategy as we used in the previous example. So we have the large space I times I, which gets quotiented to I times I mod this equivalence, which I haven't really written down explicitly, so maybe I should do this. So what is this equivalence? Well, we're identifying these points here on the border. So we think of this unit square as being embedded in R2. So we have here the origin 0, 0. Here we have the point 1, 0. This is the point 1, 1. And this is the point 0, 1. And now we need to sort of write down what this equivalence is identifying. So the first thing it's identifying is all the points here on the top with the ones on the bottom. And if you see, basically these are all the points with y-coordinate 1, and these are all the points with y-coordinate 0. So tilde here is the equivalence relation induced by the following identifications. So we're identifying x, 1 with the same x-coordinate, but now with 0 y-coordinate. So this is saying that whenever we have a point up here, this would be like, let's say 2/3, 1, we're identifying it with 2/3, 0. All right, so those are pairs of points we're identifying, and then we're also identifying the points which have x-coordinate 0 and x-coordinate 1. So this would be 0, y, and 1, y. Okay, and so with this notation here with these brackets, I mean the equivalence relation generated by all these types of identifications. So this is like for all possible coordinates x and for all possible coordinates y. Okay, so that's one quotient of this space here, and now we need to present the torus as a second version of a quotient of this space here. So this means we put the torus down here, and now we need to think about what kind of map we have going from the unit square to the torus. And well, actually the idea is sort of like already given by what we're doing here visually. So we kind of want to think about this square as being wrapped around the torus in sort of the way that's suggested by these pictures. So that would be one way to come up with such a map. So the conditions we need for the map is just that it's surjective and makes the same identifications as Q. However, sort of a more formal way to see what the map should be is to remember that the torus is defined as a product of S1 with S1. And if we now remember some maps we know from the closed unit interval to the circle, well, this is the exponential map. So in order to map a product of 2 closed unit intervals to a product of 2 S1, we just take a product of the corresponding exponential maps. Okay, so what's this map? Well, it's the map given by exp 2 pi I x, comma, exp 2 pi I y. And in this case, we're thinking of the torus as being a subspace of R4. So we're thinking of S1 as being a subspace of R2. So then if we take a product of 2 of these, we would get a subspace of R4. Now, in order to apply our universal property argument to show that these two spaces are homeomorphic, we need to show first that this is a quotient map, and second, that it makes the same identifications as Q. Now, showing that this is a quotient map is, again, easy because of the closed map lemma. So you can easily see that this is surjective because each of its components is surjective. And moreover, I times I, this is a finite product of compact spaces, hence compact. And moreover, S1 times S1, so we're thinking of this as a subspace of R4, so this is a subspace of a Hausdorff space, and hence Hausdorff. Therefore, this map here is closed, And moreover, because it's surjective, it means that it's a quotient map. Hence, the only thing we need in order to show this homeomorphism is that these two maps, so Q and this product of exponential maps, make the same identifications. Now, the way to think about this is to sort of think about how this unit square is mapped by the product of the exponential maps, and we're going to think about this coordinate-wise. So if I take some sort of two sections here of this unit square, now if we're sort of constant in the x coordinate and we're just moving the y coordinate, then this is just like this last component of the exponential map. And we know that here this is injective on the second component except for these endpoints, which become identified. So exp of 2 pi I times 0, so exp of 0 is the same as exp of 2 pi I times 1. So with fixed x coordinate, we're only identifying these 2 points in the second coordinate, and similarly with fixed y coordinate, we're only identifying these 2 points. Thus, thinking about this coordinate-wise means that any 2 distinct points in the interior of this unit square will have distinct images under this product map, because if you have 2 distinct points in the interior, well, then either their x-coordinate or their y-coordinate have to be distinct, and we know that the exponential map is injective on the interior of the closed unit interval. Therefore, also the images of one of the coordinates has to be distinct. Therefore, this product map here is injective on the interior of this unit square. And, well, on the edges, it exactly identifies things that are on opposite boundaries. If you wanted to make this more precise, you would divide into cases. So you would say, okay, if I'm in this part of the boundary, then I get identified with this part of the boundary. If I'm in this part of the boundary, I get identified with this part of the boundary, and so on. And then you would see that they're exactly the same identifications as this equivalence relation does. Okay, but I think it's pretty clear from the picture that the identifications that happen on the boundary are the same ones as given by this equivalence relation. And therefore, we can conclude that these two spaces are homeomorphic, and we're done with this example. Now, maybe here is a point where we can contrast this type of argument with the sort of from scratch argument, because if we did this from scratch, we could just define this map as we did before. We could argue that it descends to a map down here, going from this quotient to the torus. And in order to do this, we'd have to again check that this map here respects these identifications made in this equivalence relation. So we'd kind of have to do the same argument we did here with, checking that the right parts are being identified and so on. However, just because we have a continuous map here doesn't mean that we necessarily have a homeomorphism. It's just saying we have a continuous map going in this direction. Then we'd have to argue that this is in fact a homeomorphism. So in the end, we'd have to check basically the same details we checked in this argument, but we'd have to do some additional work. Okay, with that I'm done with what I wanted to say in this video. I hope that these examples give you some sense of how useful the closed map lemma can be in practice. In the next video, we'll be using the closed map lemma to help us investigate when quotients of Hausdorff spaces are Hausdorff.